Warning: this video is intended for mature audiences only. By continuing, you confirm that you are of legal age to access this content, meaning 18 years or older in most parts of the world, or 21 years or older in the United States. Working with such equipment involves serious risks, including electric shocks, burns, exposure to toxic substances, and other dangers. Do not attempt this at home unless you have the knowledge, experience, and proper equipment. Void Electronics assumes no responsibilities for any damages, injuries, or fatalities resulting from attempts to replicate the demonstrations in this video. Proceed at your own risk. Hello and welcome to Void Electronics. In today's video I will attempt to fix this Tektronix 515A oscilloscope. Actually, I've worked on this before on my Romanian channel where I fixed the trigger circuit. And I also replaced all the main electrolytic capacitors. However, I was still left with an issue that I wasn't sure how to fix, until now that is. Because now I have a few ideas that I want to try out and hopefully this will be a successful repair by the end of this video. So let's get started. Now today's issue is the perfect example why blindly replacing all the electrolytic capacitors may not fix your circuit. As you can see, all the capacitors are brand new and we still have this ripple on the vertical section of the oscilloscope. Which means that we really need to do some systematic troubleshooting in order to find the root cause and find the solution for it. Let's see how we can do that. First of all, I think it would be a good idea to see what frequency this ripple is, because this will be a clue for our troubleshooting procedure. So yeah, let's look at this. It looks to me like it is something related to the mains frequency. I think this is actually the mains frequency here in Europe, which is 50 Hz. So in order to make sure that this is the case, we can trigger the oscilloscope on the line frequency, and we can also change the trigger polarity to see if the waveform inverts. And if you look carefully, you can notice that it does. So this is exactly 50 Hz. This is the mains frequency. And we can also notice that by looking at the time per division here and doing the math for the frequency. So this gives us 50 Hz. So let's see how we can find the source of this ripple. The easiest cause of this would be related to the input. So I think it would be a good idea to eliminate this at first. So let's try to short out the input, or actually connect 50 ohm termination, because this is easier, to make sure that the ripple doesn't come from here, even though this is let's say close to impossible. So input number 2 is selected here, and as you can see it is a bit sensitive, so by getting my finger near the input we can see some extra noise. But yeah, let's try the 50 ohm termination and see if this goes away. Now it changed the offset, but the issue didn't go away. It's still here, so this means we need to do some more troubleshooting. And another thing that we can do here is to change the vertical sensitivity and see if the ripple changes with that. So we are at maximum sensitivity here, 50 millivolts per division. And we can go all the way up to 20 volts per division and it doesn't change. It has exactly the same amplitude, so I would call it, I don't know, half of a subdivision or something like that, which is, I don't know, the scope is definitely usable, but this is really annoying to me, so I would like to get rid of this. Now in order to get rid of this issue, we have to study the manual, look at the vertical section and see how it works and how we can test it. Because as you can see right here, the ripple only shows on the vertical axis. And just to make sure, we can put the scope in XY mode and kind of have a look at the dot. Okay, now we are in XY mode, let's focus it. And yeah, I guess this is really hard to see, but the dot is kind of oval and it moves up and down. And if you don't believe me, you can take a quick shot at it with a high-speed camera. Like even the high-speed functionality of my mobile phone will help here, and it will show that the dot only moves vertically, not horizontally. So this gives us a clue that we only have to look at the vertical section. Here's the schematic of the vertical section, and now I'll be honest with you, depending on your level of expertise, this will take you more or less out of your comfort zone. So explaining it from scratch is beyond the purpose of this video, so in order for you to follow along, it would be nice for you to have a basic idea of how a vacuum tube operates and also which configurations it can be used in. So if you're not familiar with that, you should maybe study this from other resources and then come back to the circuit analysis. Anyway, just like almost all scopes, I guess, the input goes into an attenuator. And of course, this attenuator has multiple steps depending on the setting on the front panel, so this is achieved right here in the left side of the schematic. And since the setting of the attenuator doesn't matter, we don't care about this section at all. So we need to look for the root cause somewhere in the active part of the circuit. So by looking at it, you will notice that this one is pretty symmetrical, which indicates that this is a differential amplifier. And it makes sense because the deflection plates that go to the CRT, that are part of the CRT, actually need to be driven differentially. So as one voltage goes up, the other one needs to go down. That's why we have a differential amplifier here. However, there are multiple reasons for doing that, and I think this also helps minimizing stray capacitances, stray inductances, and so on, and it would be better for driving this delay line that we have here before the CRT. So yeah, by going back to our inputs, one input of our differential amplifier is the actual input of the oscilloscope on the front panel, and the other input goes to a potentiometer that cancels out the offset. So in an ideal world, all these tubes would be identical and the amplifier would have zero offset, but of course the tubes are slightly different between one another, which creates an offset, and with vacuum tube equipment it's really hard to get the offset down to zero, so we have an adjustment for this on the front panel. And we can cancel out the offset using this potentiometer right here, which is also on the front panel, and it can be trimmed using a flathead screwdriver. Moving on, let's look at the first gain stage that we have here. So if you notice, V330 and V340, they both have the anodes to fixed potential, which is plus 100 volts. The input is coupled through the first grid and the output is coupled through the cathode. Of course, this being symmetrical, it applies for both tubes. So this configuration is a pair of cathode followers. So by looking at each of these tubes, each one is your basic cathode follower configuration, but since this is a differential amplifier, we have two of them, one for each side. Moving on to the next stage, or actually, you know what, let's talk a bit more about the first stage. Since this is a cathode follower, this has no voltage gain, so the voltage gain will be 1 or slightly less than that, but it has current gain, so the output impedance of this stage would be lower than the impedance, the input impedance, which will help in this case because this will help drive the next stage. So this is all that this does. We have a nice low impedance to drive the next gain stage. And now the next gain stage right here is something a bit different. So once again, the inputs here go into the first grid of V350 and V360. The anodes this time are not connected to a fixed potential, but they are connected using some peaking coils to and some resistors to a fixed potential. So this configuration is obviously different, and the cathodes are connected through some various resistors and potentiometers to a negative potential of minus 150 volts. So this configuration is more or less of a differential pair, where each side resembles the common cathode configuration. So this actually provides amplification. And the output of this stage is coupled through these peaking coils to the next gain stage. If you understood the first part of this circuit analysis, then you probably know what this is, right? Let's have a quick look at this. Well, the anodes are more or less connected to a fixed potential here. The input once again goes into the first grid of both tubes, and then the output is coupled from the cathodes. So once again, these are cathode followers, one of them for each side, of course. The cathode followers are coupled through some more peaking coils to the next gain stage, which is V390 and V400, and this is the gain stage that actually drives the CRT through a delay line. Once again, peaking coils on the anodes. We have two resistors close to the CRT that bias the anodes to 300 volts, and the cathodes go to ground using some resistors. So once again, this is more or less of a differential pair, with each side resembling the common cathode topology. That's because the cathode stays at a relatively constant potential, while the anode is where the output is coupled from. In this corner we have some more tubes, but we don't care about these. This is basically the signal that goes to the trigger circuit. So here we have some buffers or amplifiers or whatever you want to call them that take the vertical signal, or basically the amplified input signal, and couple it into the Schmitt trigger on the trigger circuitry. So this one is probably fine. This was fixed in a different video, so we don't care about this. We basically only care about the main signal path of the vertical section from the input all the way to the output. So now that you have a vague idea of how this works, you probably have some troubleshooting ideas too, or we are one step closer to that. That's because we can monitor the signal using an oscilloscope after every single gain stage right here and notice where the ripple comes in. Maybe this is one way to find the root cause of this ripple, but I think an even better way to troubleshoot this ripple is to not use any sort of test equipment at all. That's because we have vacuum tubes here which are socketed, which means that we can simply take them out one by one and see if we find a configuration where the ripple just goes away. Let's start with that. Now let's see where to find this circuit physically on the chassis. So if you remember the tube designations from the schematic, you can simply have a look at the chassis and see where that circuit is located. And it turns out it's right here. So the first pairs of cathode followers were V330 and V340, which are right here. So this is basically the first stage. And then we'll have a differential pair of pentodes, which is right here, V350 and V360. So these two. Then they go into a double triode, which is V370A and V370B, which is right here. Then they go into two pentodes, which are V390 and V400. And then the amplified signal goes to the CRT. So let's remove the first cathode followers and see if this fixes the issue. Of course, the circuit will no longer respond to the input, but we don't care at this point. We just put these somewhere safe so they don't roll off the table. That would be really nasty because, yeah, I'm in Europe, these are American tubes, so they are a pain to find. Okay, and one more thing before turning it on, you should never swap tubes at random in such a scope, and that's because the tubes are actually tested by Tektronix and they have tighter specifications than your average tubes. Not only that, but they were individually characterized and they are probably matched pairs. So please put them back exactly where they were and don't change them unless you can prove that they are faulty, because otherwise you will create extra issues and of course you will throw away the calibration. So with this in mind, let's turn it on. Let's have a closer look here. Well, this definitely didn't fix it. So the line is fuzzier right now, but it still has a ripple on it. So the ripple comes from a different stage. Let's put the tubes back exactly where they were and move on to the next stage. So once again, this one was right here. And this one was right here, so yeah, you really have to try hard not to swap them because that would be bad. So let's move on to the next stage. This is the differential pair, the first differential pair, and look at that, we have a perfectly straight line. So I think the issue comes from this stage. Now this is really interesting. Let's move on to the next stages anyway and see what happens. The next stage consists of V370. This is a dual triode, so it has both sides in a single tube. Once again, this is a pair of cathode followers. Okay, and this gives us a really fuzzy line, and of course it doesn't have ripple on it, and that's because we've basically decoupled the presumably faulty gain stage from the CRT, because one tube is missing. So I think so far things make sense. This is perfectly straight, there is no ripple on it whatsoever. It's time to put it back and move on to the next stage, which we can do just for fun, even though it doesn't make much sense at this point. This one is out and this one is out as well. So these are the tubes that actually drive the CRT through the delay line. And it would be pretty much impossible to have ripple in this configuration, but yeah, as you can see, we get a fuzzy line, but this fuzzy line is perfectly straight. So let's probe the signals inside and see if we can confirm our hypothesis. So far it looks like the first differential pair is faulty. Now with the scope on its side, we can potentially troubleshoot the vertical section by testing the vertical signals using a different oscilloscope. However, we face a new challenge here, and that's because at a first glance this circuit looks like a complete mess. Since this doesn't have a PCB with designations on the silk screen or something like that, navigating through it is pretty intimidating at first. However, this being Tektronix, of course it has the tube numbers on the other side of the chassis as well, so don't worry, every single tube here has its designation and also the tube type. And we also have the designations for the main filter capacitors, so we already have a clue how to navigate here. And also there is a systematic approach to this as well. And the key to navigating through such a circuit is to, of course, know your vacuum tubes. So what you need to know about them is, first of all, the schematic symbols for triodes and pentodes in this case, how all the elements are named and which is which, of course, on the symbol. And then you need to know your pin numbering and how it works on vacuum tubes. So there is a simple way to do this, which is to keep the tube with the pins pointing towards you and also with the missing pin facing down. So you have to hold it like this, and then the bottom left pin is pin number 1. And now the pin numbers increment clockwise. So this is pin number 2, number 3, and so on all the way up to pin number 9. So this is how pin numbering works. And of course the sockets in such a scope are numbered as well. So if you look really closely, you can see and read the pin numbers right on the sockets. And then you have to map the numbers from the schematic with the numbers that you can see physically on the chassis, and that's how you can initially navigate through your circuit. And after that, of course, if you're not looking right at the vacuum tube or around it, you need to follow the components that go from tubes to wherever you're trying to troubleshoot something. So this is how you can navigate through something like this. And of course, it makes things easier if you have a color code decoder for resistors, or if you know the color code by heart, of course. Anyway, based on what we've seen so far, once again, this is the first stage, second stage, third stage, and the fourth stage. So they increment from front to back. So it's really laid out in a logical way. What we need to do is to probe the signals after the first stage, which is after the first pair of cathode followers, to see if we have any sort of ripple there. And since this is a differential amplifier, I think it would be a good idea to load down both channels in the same manner. So I'm not going to connect the oscilloscope to just one of the sides. I want to connect it on both sides so we have equal loading and we don't create extra imbalance in the circuit, because this could potentially cause even more ripple and throw off our troubleshooting procedure. Also, I think it's a good idea to probe for the power supply voltage of the whole amplifier, so we will do that too. So let's probe into the circuit, and before doing that, let me remind you that there are lethal voltages all around this chassis, which means that it can both kill you and your oscilloscope. So you have to be really careful and unplug the scope before messing around with it. That's in order to protect you, and in order to protect your oscilloscope, you have to check the maximum voltage that is supported by your scope, and it would be a good idea to use 10x probes. So once again, we are troubleshooting the second stage, so we have to look at its input and also at its output. Let's start with the input, and in order to do this we have to test the first grid of V350 and the first grid of V360. So let's identify the tubes first, and they are right here. We have the designations on the chassis, and then we have to identify the pins. So based on the schematics, the first grid is on pin number 2. So we have to identify pin number 2 on the top tube, which is almost impossible to get on video, so I'm really sorry for this. In this case, the missing pin is upwards and we have to count clockwise. So this is the first pin, which you probably won't be able to see on video, and this is the second pin, which also goes to a resistor and to a peaking coil or something like that, which makes sense according to the schematic, and I can physically see those components right at the top part of the chassis. And then we have to ground the probe to the nearest ground point. So I will use this aluminium bar here and just hope for the best. Okay. The next thing that we need to do is to take the second probe of the oscilloscope and connect it to the first grid of the other tube on the other side, which is this one. Let's see where the missing pin is, and it is right here, and from that we have to count 2. So this is 1, this is 2. Pin number 2 is right here. You always count clockwise. And we also have to ground this probe, and I will also ground it to the same aluminum bar. And now, using the third probe, I think it would be a good idea to test the supply voltage of this stage, which, after following the wires from the anodes, it turns out that they lead here. This is hard to see on camera, but here's the filter capacitor for this power supply, which is hidden right near the ceramic strip right here, so you won't be able to see it on camera probably, but we have a filter capacitor between this terminal and this terminal, which is grounded. It's a flat ceramic capacitor that stays right against the ceramic strip. So with this setup in place, we can test the input of this gain stage and also the power supply. Once again, be careful not to fry your oscilloscope with this. So I'm starting with 50 volts per division, AC coupled, because we basically don't care about the DC component, we only care about the ripple. Let's turn it on and see what we get. So we have some movement there as the tubes warm up, and after it settles, I think it's a good idea to increase the sensitivity and look for ripple. Okay, so on the first channel and on the second channel, which is the yellow one and the violet one, we have the differential signals, and the power supply is on the third one, which is the blue one. Let's increase the sensitivity and look for ripple. We are at 100 millivolts per division, and this one looks very clean. Let's do the same thing for the other channel. Once again, this is very clean, and let's do the same thing for the supply voltage, which is not as clean, but I would say this is good enough. So as you can see, at the input of this stage the signals are pretty much perfect, they are very clean. So it's time to move on to the next stage. So using the same approach, we have to disconnect these probes. Of course, the scope is unplugged, and now we have to identify the outputs of this stage, which apparently couple into the next tube on pin number 2 and pin number 7. That's because this is a dual triode, and pins number 2 and number 7 are the first grids. Using the same convention, I hope, the first channel goes to pin number 2 on this tube. 370 is right here. This is the missing pin, and then we count clockwise once again. So this is 1, this is 2, and we have to connect the probe right here. And then the second channel goes to pin number 7. So we can count starting from pin number 9. This is 9, 8, 7. So once again, this will be hard to see on camera because I think pin number 7 is beneath this fuzzy resistor. Okay, let's repeat the test. Okay, we cannot see much on 50 volts per division, of course, but we can change the settings and have a look at this once again. So let's go to 100 millivolts per division once again, applying the same settings as before. And now there are two annoying things happening. First of all, we see the ripple, and we also see some noise that comes from the desk lamp. So I really hate this lamp because it messes with all the analog circuits. Look what happens when we turn it off. The signal is much cleaner, but this indicates an issue, and this confirms what I've just said. So as you can see, after the second stage we get some ripple, and what's worse is that this ripple is not symmetrical. So we have more ripple on one side than the other, and I think this is differential mode ripple. So let's see. In order to see what this is, I think it's a good idea to use the math channel and just subtract channel 1 from channel 2. And the difference actually is channel 1 minus channel 2, which is right here on the scope, and it looks like a sine wave, which is the ripple that we are trying to get rid of. With this in mind, let's have a look once again at where the channel number 2 goes, and this way I think we can identify the fault. So I really think we are onto something right now. I think we are looking at a bad tube. So going back to the schematic, the second channel goes to pin number 7. Pin number 7 on V370B is driven by V360. So presumably V360 is faulty. Now the good news is that my friend from Gears and Gear, which is a really nice YouTube channel, provided me with some spares for this oscilloscope. So the tube is already out, as you can see, and this is a new tube that we can try out to see if it solves the issue. Now this is a tricky thing to do because, as I said, these tubes need to be matched. So it's a good idea to match the tubes on some sort of test equipment, like a tube tester, ideally one that tests for the transconductance, not just the emission current, or even better, it would be to match them on a curve tracer. To be honest, I didn't do any of these. I'm just swapping tubes at random, which is not recommended, and we will have to figure out whether or not this works based on the waveforms. Okay, the new tube is in, and before turning it on, let me remind you that before we had like 50 millivolts peak to peak of differential mode ripple. Let's see if this gets any better. I'm really eager to see what's going on. I hope we can fix it. Of course, we need to wait for the tubes to settle, and we will see weird things happening on the scope until that. And now the circuit slowly turns back to life, and let me tell you, it looks a lot better already. Yes, I think we fixed it. It looks a lot better. So we have something like, I don't know, 20 millivolts of ripple or something like that, but that is mostly probably mathematical ripple from the oscilloscope or something like that. It's not really, I mean, it's not really ripple, it's pretty much noise. And we can see that it also has a ripple component, like a 50 Hz component to it, but I would say this is a lot better. So let's have a look at the trace. Now, strangely enough, the trace is missing, so if this happens to you, don't worry, you haven't killed the oscilloscope. It's just that due to a different tube, we have a wildly different offset, and now the trace is somewhere out of the screen. So let's see if we can bring it back using the vertical position. Okay, we cannot do that, so what we need to do is put the vertical position right on the middle, and then adjust the DC balance that I've talked about in the beginning of this video. So this one will cancel out the offset, and we should be able to bring the trace back. Here it is, and it looks really nice. We finally fixed it. Oh, I love it. This is so nice. Look at this. We have a perfectly straight line. And now that the scope looks okay, I think it's time to feed it some signals and have a look at the differential signals using the other scope, because this will indicate how good the matching is between the two tubes. It's probably not perfect, but I suppose it will be good enough. So to do this, I'm going to put this scope to the ultimate test by using a really fast pulsar. Now this is a pulsar that was initially designed by Jim Williams, and it was redesigned by my friend from Gears and Gear once again. So yeah, thank you really much for this PCB. It's a really nice piece of kit. He also gave me this 50 ohm termination as a gift, so these really come in handy for testing this oscilloscope. So let's connect this right here. This pulsar, by the way, creates some really fast pulses. They have a rise time of around 300 picoseconds or something like that. So this takes the scope way out of its comfort zone, and we can see how fast the circuit is and how it reacts to fast signals. And we can even estimate the bandwidth of this oscilloscope based on that, but this will be a topic of a different video probably. So let's select this, turn the pulsar on, and now the signal is so fast that we don't see anything, so we need to do a few things here. First of all, we need to increase the sensitivity until we start seeing something, and now we need to turn the time base all the way up, of course, and trigger it on internal positive, and we get a pulse, believe it or not. So now, even though this scope only has a bandwidth of around 15 megahertz, it can actually see the signal. So I think this is amazing for vacuum tube stuff. I don't know, it's hard to express in words how amazing this is, because we can see this only because the circuit is absolutely genius and because it has a delay line. So we can see the pulse already, and if you want to see the pulse even better, we can turn on the 10x magnification, and look at that. I think that's so beautiful. So yeah, let's compensate for this with some more intensity, increase the sensitivity, the vertical sensitivity, and here it is, a really nice and relatively clean pulse. And now we can have a look on the oscilloscope to see what the differential signals look like. Sorry that you cannot see the pulse properly in the video, but yeah, let's change the horizontal position so that you can see it better. Let's see if this looks better on video. I think you can sort of see it. Now, of course, the settings on this scope are way off for what we're trying to get. So first of all, I think we need to decrease the sensitivity. Let's say 1 volt is okay for both channels. And then the time base needs to be a lot faster than this, obviously. And we can start seeing the pulse right here at 1 microsecond per division. And we can go even faster to have a look at this just a little bit better. Here it is. And yeah, they're pretty symmetrical, I guess. I don't know. I guess they're close enough. Let's offset them just a little bit more. Yeah, they're not perfect, but hey, for such a fast signal, I think this is more than enough. Let's have a look at the power supply as well. Let's see if it's stable. And it's not even close to being stable. Of course, it rings like crazy. So I don't know if should we take care of this or should we ignore it altogether. Maybe it needs a snubber, but yeah, I'm not in the mood for fixing this as well. Let's see if we can get the math channel back. Okay, it's right here. It's way off. Let's adjust the math channel and maybe you can see the pulse. It's upside down. Okay. So yeah, we can see the pulse, and it more or less resembles what we can see on the vacuum tube oscilloscope. So you can see the matching between the tubes is probably not perfect. This is a little bit asymmetrical, but I'm pretty sure this will give us acceptable results. So that's about it. Here's what the trace looks like after the fix. As you can see, it's a perfectly straight line. I just love how it looks, and it's also incredibly thin. There are scopes that have a much fatter trace, even though they are like a few tens of years younger than this one. So I don't know what they did and how they did it, but yeah, there is some amazing engineering behind these scopes. For comparison, this is what the trace looked like before. So as you can see, the improvement is huge. Once again, here's what the pulse looks like after the fix, and I think this is just amazing. It is amazingly stable and it looks beautiful, and it's not fuzzy at all if you tweak the triggering settings just a little bit. I'm pretty sure that if we do the math here for the rise time and everything, this exceeds the specs of the scope, so I would say that we did a really great job in this video. So to recap, you know, this could have been a 10-second video where I just swap a vacuum tube and all of a sudden the thing works, but that's not the point and that's not what I'm doing on this channel. So I really wanted to show you a systematic troubleshooting approach for something like this, so that you can gain some troubleshooting skills yourself. So yeah, let me know in the comments if you like this video. Let me know if you want some more content based on vacuum tube oscilloscopes or something like that. And if you like this video, please give it a thumbs up. And if you're interested in more content related to electronics and programming, please subscribe to this channel because there is more content like this on the way. That's it for now. Bye.